Hello everyone, I'm Miss Rose Piazza and I'm going to be giving a talk on some research that I've done this semester that follows along the lines of my current larger research, which is threat modeling for trading deep reinforcement learning agents. The first paper, which is regarding the threat model itself for these trading agents, as well as demonstrations for certain inference attacks that are active. This particular demonstration and paper that we'll be going through will be about a type of passive of attack and whether or not information obtained from these passive attacks can be useful to an adversary. So artificial intelligence has become extremely popular, at least within the last decade, and a lot of markets have been looking at machine learning algorithms to automate tasks. Reinforcement learning falls underneath this umbrella term for machine learning algorithms, and the core of reinforcement learning is based on an idea called the Markov decision process. This process is a discrete stochastic decision-making process or mathematical framework. The goal of an MDP is to extract an optimal policy, which is a mapping from states to actions, such that the expected return is maximized. We can make an analogy of an MDP to a computer. A computer is a framework that consists of internal components that work together to accomplish a task. Similarly, the Markov decision process have components such that when they are used together, they can obtain an optimal policy. Likewise, there are variations in ways of how to obtain an optimal policy. There are 3 exact methods that are talked about, which is value iteration, dynamic programming, and policy iteration. Reinforcement learning as a field has many branches. There are quite a number of algorithms underneath reinforcement learning. They can have many properties, but generally these agents can be classified with a few properties, which are they're either model-based or model-free. Model-based is when there is a transition function that is provided that models the environment. Basically, this is a planning agent from existing knowledge. Model-free is when an agent doesn't have any knowledge of the environment, so the only way it can learn information about the environment is through trial and error. And also, model-free agents do not directly approximate the transition function. Agents are either on policy or off policy. On policy refers to when their behavior policy is used to generate experiences from the environment, which is the update policy that's being learned. Off policy refers to when the behavior policy is different than its update policy. For example, epsilon greedy is a behavioral policy, but the update policy, which is argmax, is a greedy policy. Furthermore, under model free, there are more exact algorithms or methods that determine when to update the policy. 2 popular methods are the Monte Carlos and temporal difference learning. For Monte Carlos, the policy is updated after every episode. For temporal difference, the updates are more frequent, however, there's bootstrapping. Under temporal difference learning algorithms, one particular algorithm is Q-learning. So Q-learning is an off-policy, model-free iteration method used to iterate to find optimal Q values or state action values. The particular agent we will be implementing on will be a Q-learning descendant, which is called deep Q-learning. The general concept of deep reinforcement learning is the introduction of neural networks as function approximators for at least one of the MDD components, as well as other tricks. For example, DQN has a trick called experience replay. DRL has become popular among machine learning algorithms for trading automation, resulting in agents that are profitable. As a result, there are open source libraries like TensorTrade, which are used for the purpose of deploying and training reinforcement learning agents for trading. For our demonstrations, we'll be using a deep Q learning agent. As mentioned before, this particular work is a follow-up from a previous paper on threat modeling trading deep reinforcement learning agents. This link will lead you to the paper that was written specifically, but this was based on a DRL threat model framework provided by Bezida. The DRL threat model framework outlines 2 types of attacks. This is when an attack occurs. The inference attacks are referral to test time attacks, and training attacks are usually generally referred to as poison attacks. There are 2 general types of inference attacks, which are active and passive. The first paper demonstrates some active attacks. We will be looking at particularly how useful information gathered from a passive attack may be used. Of course, we're going to have to make some assumptions, like how much information we will be gathering, whether or not this information is perfect, and how useful is imperfect information. So let's say an adversary is able to obtain some experiences of the agent. What can be done with these experiences? Well, One particular branch of reinforcement learning is imitation learning. And the general development of imitation learning methods have always been used to mitigate early stages of training, which tend to be destructive for off-policy agents. One particular imitation learning variant that we'll be looking at is deep Q learning from demonstrations. Likewise, we'll be following the adversarial perspective of IR methods introduced by Bezadon and Husu. The basic idea behind deep Q learning from demonstrations is that one, an agent is trained on demonstrations we assume to be optimal, like an expert. We call this the pre-training phase. And then two, after the pre-training phase, the agent is allowed to interact with the environment to generate its own experiences. However, it does prioritize the expert's experience over its own. And more specifically, DQFD has a different type of loss. It is the sum of four losses, which is a double DQN one-step look ahead, a double DQN n-step look ahead. In our particular execution, we'll be doing a 10-step look ahead, a supervised margin loss, and an L2 regularization, which is applied to the model's parameters. The intention of the supervised margin loss is to put the expert's actions over its own, as well as penalize for any actions that are not the same as the expert's actions. The general DQN loss uses the same neural network to select an action as well as regress the Q values. This can be problematic, which is referred to as the maximization bias. WDQN loss is used to separate the selection of actions as well as regression of Q values by leveraging the target network and the policy network. This is seen in another variant of DQN, which is called double DQN learning. It is within an adversary's interest if they intend to do white box attacks upon the target agent. They want to craft an agent that can imitate the target agent's actions. So here in this table, we have a few DQFD agents which are trained on different amount of demonstrations. As we can see, the training evaluation, which is the exact time steps which were used to train the agent, at least for the DQFD agents, they cannot necessarily replicate the same action sets as the target agent. However, we do include a behavior clone, which is a supervised learner to imitate the target agent. It proves to be very successful for the training evaluation. However, for all agents, for the randomization evaluation, which is data that is not seen by any agent, in other words, unseen states, their performance are not necessarily parallel. However, if an adversary's intention is to gather demonstrations to train their own agent to use, then it is possible for them to train agents from demonstrations that perform competitively, both in the total reward performance metric as well as the network gain. This network gain is calculated from an external portfolio that the agent has access to. Additionally, we would want to know how useful imperfect demonstrations are. Imperfect demonstrations, we refer to them as non-continuous demonstrations or segments of demonstrations that are missing time steps. Of course, we cannot expect them to imitate the target agent since we have even less demonstrations provided. However, can we still have competitive agents resulting from DQFD using these imperfect demonstrations? And in our demonstrations, we do have agents that can still perform competitively well against the target agent. However, it is extremely difficult to generalize these results to other complex trading environments. Which leads us to a bigger conversation about the expectations for reinforcement learning and DQFD. RL has been showcased for MTPs of completely seen states, for example, the Atari game Breakout. All policy model free DRL agents can perform generally well, where states can be frequently visited since neural networks have large memory capacity. It is unlikely agents who generalize better to unseen states learn an optimal policy with respect to the training, or it is also unlikely agents who learn optimal policies for training are optimal for testing on new states. This generally can be seen for deployment of neural networks that do relatively well in training as well as validation, however do not return the same results when deployed in real life. Additionally, the MTP is an assumption made during the start and duration of training. Any changes such as the terminal state can change the trajectory as well as the optimal policy for an MDP. Of course, depending on the condition on what constitutes a terminal state, in the case that an adversary is able to intercept some demonstrations, however is unaware of the actual terminal state, the resulting policy gain may not be the same as the target policy, especially if the terminal state changes during additional training. Our best agent that can imitate the target agent for at least the training evaluation would be our behavioral clone, which is the supervised learner. However, our behavioral clone would generally be unstable due to the violation of the Bellman optimization equation. However, we can still train agents on these demonstrations that are competitive to the target agent. Furthermore, we have several agents that we can use for white box attacking, such that we can test transferability of our white box attacks to the target agent. So here we have on the right a table of our DQFD agents as well as our behavior clone under transferability to the target agent. The particular type of attack that we will be doing is an FGSM non-targeted attack. The successful attacks are when the white box attack has been successful in changing the action of the imitated agent, then the perturbed tuple is saved and then inserted into the target agent during its iteration of its randomization evaluation. No attack needed refers to a time step of a previous inserted tuple that affects the action taken at a particular time step without the insertion of a current perturbed tuple. The results of this table can show that there is a level of transferability of the white box attacks that we have implemented to the imitated agent that reflect upon the target agent, showing that in some sort of way these agents are similar. Furthermore, we can make commentary on the DRL agent's observation space. Since the observation space is a moving window of 3 values, which are the high, low, and close price, it is both susceptible and robust to adversarial attacks. These agents are robust because the convolutional neural networks have been stated to be more robust against adversarial attacks. They are also robust because a single tuple of values inserted at the beginning of the window generally did not change the target actions at the particular time set it was inserted. However, these agents are also susceptible because the moving window of past tuples allow perturbations to stay in the succeeding time steps longer. And also is susceptible because some dimensions are more or less sensitive to perturbations. However, it is extremely important to know for man-in-the-middle attacks, they are either successful or not. The presence of perturbations tuples in the observation space will generally impact the future time steps regardless if the perturbation tuple changes the target's actions upon insertion. Such models need adversary resistance and robustness. And here are the wonderful references. So here we are in a IPYNB notebook, so a Jupyter notebook, where all my code is stored. These agents are generally written in Python files. However, I put them inside of a notebook to make it easier to run for the explicit implementation and purpose of debugging. So this is the general framework of it. It has a demonstrate method such that we can record the demonstration. So this is the target agent, and then it's demonstrating some experiences and they're saved. Skipping. These are the other demonstrations for other percentages for the discontinuous time sets, the imperfect demonstrations. They're loaded in, they're saved, and also they're saved and put into an NPY format. Then they're loaded back in just for reiteration purposes of after this executes. This is the pre-training phase. Pre-training phase, which applies this particular loss for updating the policy. It's a little long. There's the 4 losses. There's the 1 step look ahead, double DQN loss, n step look ahead, double DQN loss, the large margin supervised loss, and then I left the regularization L2 loss to be used on the neural networks. This is some of the losses. This is the pre-training phase. All it does is it updates the policy and it copies over the policies to the target network every so often. And also this particular memory, it is a partition memory such that it prioritizes the expert demonstrations. Test is just a particular piece of code that sees how well or demonstrates the agent in a continuous time steps of how many you want, and you can see and inspect how it performs in terms of total reward as well as impact on portfolio. So here's another little skeleton to make it easier when training all the other agents, because after a while you would get too many blocks of code, so it would be easier just to put it all together. So that's one agent. And then you can test it on 250 time steps, for example. Goes on and on. Here. Okay. So then now we have randomization start. So this is the randomization evaluation. And the reason why you would want to use slices instead of just at any particular observation is because you still want to keep track of how these external portfolios are impacted by these agents. Yes. Additionally, the code to run the perturbation can be found here too for the transferability. Right. So let me move over to another notebook to show you another way that can be written for it to make it easier for the graphs that we included in regards to accounting the imitation action that matched with the target agent for these imitated agents. So we have some recording of observations. This one says 500, but it doesn't have to be 500. It's whatever you want. Then it goes through all the agents and it says, and then it shows the target agents, it shows the imitated agents, the observation. If it is successful, then it is shown to the target agent. If they are the same action, then it's a match and it counts. So this is how the count is done. Alternatively, you could do it for the entire data set if you want. And yeah, these are the results from that we've seen in the paper. And then also, if you want to preserve randomization, it can be this way. However, if you strictly want random observations from the observation list, then you could just run, I have it here somewhere. Here, you could run it here. So this has all the observations. So it's 8,000, then it picks a random choice using the range, and the time step is what we would pass through, saying like how many random observations you want to pick. This is the results. It's not very convincing when you do it this way, which is to be expected. All this code and necessarily will be released at some point after some things get solidified, and then it'll be attached to the research page on the Sail Lab homepage if you're interested in looking at some of the code and implementing something yourself. Thank you, and I hope to hear some questions.